as we wrap up our discussion of derivatives, we need to take a look at the meaning of higher derivatives as well as implicit differentiation. Higher derivatives are used to talk specifically about your speed, and when your speed changes, then your acceleration. We're not going to be using any new derivative techniques. We're simply going to put to use the ones we already have. So when I have an original function like x squared, if I wanted to know the speed at which the car was traveling at any point, I could find the first derivative, and 2x represents the speed or the velocity at which I was traveling. So if you imagine x squared looks something like that, for any point we pick, the x-axis would be our time, the y-axis would be our distance, and to find the speed that I was traveling at this point, I could simply plug in what time it was and I could find the appropriate speed. And we're familiar with the discussion of speed because our cars travel at a certain speed. It's how many, for example, miles that you can travel per hour or per minute, that type of thing. Remember, when you're talking about speed, you do always have to have a unit with that. Now, if we take the derivative of the derivative, so if I take the f prime of x equals 2x, and I find the derivative of that, well, the derivative of 2x is simply 2. And we write it by just giving a double tick mark. And so the derivative of the derivative. So what we're asking is, we know the speed, and I'm asking for the rate of change of the speed. The rate of change, how fast is my speed changing? And that's called acceleration. In other words, when the red light turns to green, do I gun it or do I slowly increase my speed? That's acceleration. The fact in this case that it's a 2 says that you're pushing your gas pedal consistently. You're not going to push it faster and then let off. Okay, so this says if these are miles per hour up here for the speed, this would be miles per hour per hour. So the speed is changing per hour. And if my acceleration is 2, if I start out at time 0 and I start accelerating at 2, at the end of 1 hour, my speed will be 2 miles per hour. At the end of 2 hours, I'm going to speed up some more because I'm accelerating my speed by 2 miles an hour every hour. So now my speed is going to be 4 miles an hour. So this 2 is working in here, that as it improves, it's adding 2 miles per hour to the speed. And so now not all accelerations are the same. Think about when you drive a car, you don't always push that gas pedal perfectly consistently. Sometimes you let up, sometimes you go faster. But that's the idea behind it. So whenever you take the second derivative, you are finding acceleration. You could also take the third derivative, and it can also be written like this. Notice with the first one, the 3 is with the derivative, so the third derivative of f in respect to x all 3 times. That's what that says. The third derivative of x, of the function, with respect to x all 3 times. To take the third derivative, you simply take the derivative of the second derivative. So to do the third derivative of 2 is 0. So let's do just one other example so that you can see it's not always a constant so quickly. What if we started with f of x equals 2x to the 7th plus 3x squared? So the first derivative, we multiply by 7, so it would be 14x to the 6th plus 6 to the x, or I'm sorry, 6x. That's the first derivative. That represents the speed. The second derivative, we would do 14 times 6, which I hope is 84, x to the fifth, and 6x would be 6. That represents the speed, the acceleration. I could continue. The third derivative, we're going to do 5 times 84, which is 5 times 80 is 400 plus 20, so 420x. To the fourth, notice that the derivative of 6 is 0, so that's gone. And I could keep going. We use Roman numerals here. We're going to do 4 times 420, x to the third, and eventually it will get down to 0. We typically focus on the first derivative and the second derivative, speed and acceleration. If you take the derivative of the acceleration, you're asking how fast is the acceleration changing? And back over here, where the third derivative was 0, this says that the acceleration is not changing because it's 0. If that were a number, then that would tell you what you were doing to the gas pedal. How were you pushing it? Were you letting it go? That type of thing. So higher derivatives use the derivative techniques, but it gives us some more information about the what the equation represents. Now, let's take a look at implicit differentiation. Implicit differentiation is not that hard if we can understand one basic concept. And I'm going to try right over here where I'm drawing this red line. I'm going to try to hit that concept here, and if you really need help with it, please contact me so that we can make sure you understand this. We perhaps, when we started taking derivatives, if we hadn't kind of shortcutted one thing, it might have been easier now, but it would have made it more difficult back then. So I'm going to try to make a connection. We had an equation like y equals x. And we took the derivative of that. Now what we did was we simply did something like this. dy dx equals 1. Or we wrote y prime equals 1. Okay? Now that's great, but if you remember back to good old algebra, where when you do something to an equation, what you do to one side, you have to do to the other. So technically, here is what we did, though we didn't write it. I'm going to switch colors. Is we took the derivative of y with respect to x. That's this, the bottom says with respect to x. This says, the D on top says take the derivative of y. The bottom says with respect to x. Let me put that in context. Tell me how your distance is changing as your time changes with respect to time. So I could say the derivative of your distance, which is your y value, with respect to time, which is your x value. That kind of, I think, helps it make sense. The derivative of the distance with respect to time. How is your distance changing in respect to how time changed? I could ask, how's your distance changing in respect to what you ate for dinner? I mean, you can ask that question, but there may not be any relationship. So that's what dy dx is saying. This is just an example of that. Well, if I'm going to do d over dx on the left, I have to do d over dx on the right. So on the right, it's saying, how is x changing in respect to x changing? Well, if x goes up 1, what does x do? It goes up 1. If x goes up 4, it goes up 4. So this is asking, how is x changing in respect to x changing? Well, it's a one-to-one relationship. dx over dx, anything over itself, is 1. We found that by looking at the slope of y equals x. The slope of y equals x was 1. That's how we kind of developed that. But that's really what's going on, is that you're taking the derivative of both sides. The derivative of x with respect to x is 1. That's the piece I need you to truly internally understand. that if I'm asking you, how is your weight changing for every pound that you gain? That's really what dx over dx is saying, is what is your change in weight if your weight changes? Well, if my weight goes up a pound, then my weight changes by a pound. And so dx over dx is 1. If you can be okay with that, then we can go on to implicit differentiation. So anytime you take the derivative of y with respect to x, that's not something that equals 1, because as x changes, y may be changing differently. But when you take the respect of x with respect to x, or the derivative of a with respect to a, or anything that matches, that answer is 1. So now we go over here and we attack something that has lots of variables. I'm actually going to start with a simpler example than the two listed here to help you get that concept. But a variable is a variable is a variable. Let me show you this. We have these two variables, y equals x plus 2. We have an x, we have a y. We've been taking derivatives of that for several weeks now. Let's take the derivative of both sides with respect to x. Now, it is possible to take the derivative with respect to y or with respect to anything. It kind of depends on what your independent variable is and what your dependent variable is. Well, dy dx is simply dy dx. Then we have the derivative of x with respect to x, and we have the derivative of 2 with respect to x. We have never written this like this before, but it's what we did. Dy dx, can't do anything with. Dx dx is 1, based on our conversation earlier, and the derivative of 2 with respect to x is 0. So my final answer is 1. Now that's the way we've been doing it. But now if you notice in these tougher examples, the x's and y's are all mixed together, and there's no way to get them by themselves. Okay, so let me rewrite this and make this x minus y equals 2. This equation and this equation were the exact same equations. So now I'm going to show you what implicit differentiation looks like, but using this same exact example. So when we have to do implicit, technically you can do implicit all the time. We technically, where I just drew that star, we technically just did implicit differentiation. But it was an easy one because the x and y were on opposite sides of the equation. Implicit usually implies that the x and the y are on the same side of the equation and that they can't be manipulated to be on just one side. And you've got to be careful because sometimes it looks like you can manipulate, but what you're creating is a new function that does not match your original. And you would almost have to look at the graphs of them to determine if they were exactly the same. So here's what we're going to do. We're going to take the derivative of this side with respect to x and the derivative of this side with respect to x. So I'm going to distribute dx over dx minus dy over dx equals the derivative of 2 over dx. Now I'm going to take the derivative of each piece. Dx over dx is 1 because the derivative of x with respect to x is 1. Minus dy dx, we don't have a value for that because the change in x will influence the change in y, and that's what we're trying to find out, is how does a change in x influence a change in y, and the derivative of 2 with respect to x is 0. Now we simply need to solve for dy dx. I'm going to move this to the other side since it's negative, and we get 1 equals dy dx, which is the exact same answer as we got right there. So we are doing nothing different except I just needed to revisit the idea of taking the derivative of both sides, and that we have to understand that dx dx is 1, whereas dy dx is, that's what we're trying to find, is what is that relationship. So now let's try something that's a little bit harder. You have to remember that a variable is a variable is a variable. So if you have two variables multiplied together, we have to use the product rule. If you have a variable divided by a variable, you have to use the quotient rule. So it doesn't matter what the variables are. If they're variables, we have to follow the rules that you just learned. Okay, so the first one, we have 3xy plus 4y to the third equals 10. And we're going to take the derivative of this side with respect to x and the derivative of this side with respect to x. And so we're going to distribute the derivative of 3xy with respect to x plus the derivative of 4y cubed with respect to x equals the derivative of 10 with respect to x. Now, right here we have x, or 3x times y, and we're going to have to use the product rule. So we're going to have to do the derivative of 3x times y. You could put that coefficient all the way out front and just do the x times y, whichever you would rather. So let's tackle that first. Some of you like to do the u, dv, v, du, all that stuff, and that's great. If you want to take a second and pause this and set yours up. Okay, so the product rule says take the first item, which is 3x, times the derivative of the second piece, which is the derivative of y with respect to x. Okay, plus the second item, y, times the derivative of the first item. So I'm going to write it just like that. The derivative of 3x dx. Okay. And now let's clean that up. We have 3x dy dx. And the derivative of x with respect to x, remember, is 1, but we have to multiply that by 3. So the derivative of 3x is 3, but we also have this y out in front, so that would be 3y. So there's no longer a dx here because the derivative of x with respect to x is 1. Alright, so that takes care of the first term. Then now let's do the second term, which I'll put in green, and that is the derivative of 4y cubed with respect to x. First, we follow the product rule, so we're going to do 3 times 4 is 12. We're going to reduce the power by 1, so that brings me to a 2. But don't forget that we have dy dx, and we can't just get rid of that because dy dx does not equal 1. It's kind of like using the chain rule, that you have to treat this y as a variable that you have to make sure in the end that you took the derivative of it. So that's the dy dx. And over on the right side, the derivative of 10 with respect to x is 0. Remember, our ultimate goal is to find dy dx. That's what we were trying to do by taking the derivative of both sides. So now what I'm going to do is work to get the dy dx's together. To do that, we first need to move the 3y to the other side. So I have 3x dy dx plus 12y squared dy dx equals negative 3y. Now to get dy dx by itself, I'm going to have to factor that out. And that leaves me with 3x plus 12y squared equals negative 3y. And so now I need to just divide by what's in parentheses. Dy dx equals negative 3y over 3x plus 12y squared. And I could factor out a 3 from everything and reduce, so it would be negative y over x plus 4y squared. So I factored out this 3 from everything. That is dy dx. Now, what is that telling us? That is telling us that our graph, the slope of the graph at a certain point, or the speed at a certain point, doesn't only depend on where you are for x. So if I just had this, then my speed depends on knowing where you are on x. Your speed just depends on your time. Tell me what time it was and I can tell you your speed. But what this is saying is that your speed at any point is not only determined by x, but it's also determined by your location of y. Here's what that graph might look like. Just something crazy like this. If I wanted to know your speed at this point right here, whatever this, maybe this is 5. If I wanted to know how fast you were going at 5, at location 5, whatever, it's not necessarily time. The problem is, I don't know if you want that speed, this speed, this speed, or this speed. So I've got something that's rotating in an orbit, I've got something that's just going round and round a race car track, and every time they hit this point, I want to know their speed, but their speed at A is going to be different than their speed at B and C and D. So not only do I have to plug a 5 in for x, if this were my for example, I would need to know, I want to know what your speed is at A, and that's when this was 7. I would have to plug a 7 in for all of my y's. So the reason we have implicit differentiation is allows us to find an equation for the slope of a curve that is not necessarily a function that passes the vertical line test. And so now the speed of the object depends on the location of the object, and we need both x and y. Okay, so now let me get erased and we'll look at another example. So getting ready to erase, so you may want to pause if you need to take a greater look at this. Okay, so let's take a look at this example. I've rewritten it as the square roots so that they are in powers x to the 1/2, y to the 1/2. And so now let's take the derivative of both sides with respect to x. And so let's distribute the derivative of x with respect to x, the derivative of x to the 1/2, y to the 1/2 with respect to x, and the derivative of y squared with respect to x. Now, the reason I could break up the x and not the x to the 1/2, y to the 1/2 is because the x to the 1/2, y to the 1/2 is multiplied together. That's one term. The derivative of x with respect to x is just 1. Here we have two variables multiplied together, so we're going to have to use the product rule. To do the product rule, it is the first term, and again you may want to pause to do your u's and v's, but it is the first term, x to the 1/2, times the derivative of the second term. So I'm going to write the derivative, and you don't necessarily have to write that if you're comfortable with going ahead and taking the derivative. So first times the derivative of the second plus the second times the derivative of the first, and equals, and then the derivative of y squared, again we follow the power rule, so just it's a variable and we bring the 2 down front, we decrease the power by 1, but then we take the derivative of dy dx, we can't get rid of that. Let me go back and clean up the derivatives here. Again, we have a power right. Oh, sorry. We have a power right there, y to the 1/2. So we bring the 1/2 down. We decrease the power by 1, so that would make it negative 1/2. And we still have the derivative with respect to x. And over here, we have y to the 1/2. Now we need to take the derivative of x to the 1/2, so we bring the 1/2 down front. We decrease the power by 1/2, and dx is 1, so we don't have that. This is a mess because we've got some powers going on that are negative, so let me get us some room here. So as I copy this problem over, I'm going to write things, I think it's going to be nicer if we go back to radicals. So we have x to the 1/2, which is the square root of x. We have a 1/2, so I'm going to put that out in front. And we have y to the negative 1/2, which is the square root of y in the bottom. Okay, take a second there and see if you get this equaling this. Now we're not quite done here. Let me get my line back. So we have x to the 1/2 is square root of x. We have the 1/2 that was in front of the y is there. And y to the negative 1/2 is the square root of y, but it's in the bottom because it's negative. And then we have our dy dx. Plus, we have on the next one, we have another fraction. We have a 1/2 in there. We have a square root of y on the top and a square root of x in the bottom. And so this green one should match this. And then we have equal 2y dy dx. Now first, let's get dy dx's together. So on the left side we have 1 plus the square root of y over 2 square roots of x equals 2y minus 1/2 square root of x square root of y, and I forgot my dx or dy dx. Let me put my dy dx there and my dy dx there. So I pulled this guy and put it over on the other side. Because we got a lot of fractions going on, we're going to really need to get common denominator. So first, on the left side, my common denominator is 2 square roots of x. So I'm going to have to multiply both top and bottom here by 2 square root of x. And so that's going to give me 2 square roots of x plus y over 2 square roots of x. Over on the right, my common denominator is going to be 2 square roots of y, so I'm going to have to multiply top and bottom here by 2 square roots of y. So that's going to give me 4y square root of y minus 1 square root of x all over 2 square roots of y, and we have dy dx factored out from both of those. I did a lot of algebra right there, so take a second and make sure that you caught up on that algebra, because the hard part about calculus isn't calculus, it's the algebra. Now to get y dy dx by itself, we're going to divide by everything in parentheses there. So we have to divide by the pink, and when we divide by the pink, let's flip and multiply. So we have 2 square roots of x plus y over 2 square roots of x times 2 square roots of y over 4y square roots of y minus square root of x equals dy dx. There's not a whole lot we can do here other than cancel those 2's. And we could go ahead and distribute the top and distribute the bottom. So on top, so I'm sorry that I ran out of space here, but let me go right here. So I'll have a box here for the final answer. We're going to multiply this y times everything over there. So it will be 2 square roots of xy plus y square roots of y over, and on bottom we're going to distribute this square root of x to everything. So we're going to get 4y square root of xy minus square root of x times square root of x is square root of x squared, which is just x. And that is our speed function for that. So you can see that one's quite complicated, that there's really not a lot of consistency in the speed. You would have to know the x and y location to plug it in. So implicit differentiation allows us to take derivative of curves or functions that don't pass the vertical line test. So we really probably shouldn't call them functions. But we do study the speed of objects even if their graph is not a function, and that's what implicit allows us to do. You have to remember that dx dx is 1, but dy dx is not 1. That's what we're trying to find. So work hard on these. If you can do these, you can do any derivatives there are. So good luck. Let me know if you need help.